Sure this works? Yep, works. Good. Um, so I thought I'd start out with two pictures from Ottawa and tell you just briefly about Canada. So I don't know very much about Spain, but as I understand it, it's somewhat like Spain. It's two cultures, English and French in our case, and in your case it's Spanish, I guess, Catalonian. I'm not sure what else, but and so the river right behind there and the building right there is the Ottawa River. It separates the two language groups. Um, Not exactly, but to a certain extent. It separates the provinces in which the two language groups are in. One's on Ontario, so the National Research Council building, the big building there, is in Ontario, and then the other side is Quebec, which is the French-speaking part. Not completely. There's a mixture of people, but not complete mixture. Okay. The building itself, National Research Council building, might seem familiar to you. I don't know. Canada is a very young country, and this is the first major lab ever built in Canada in 1929. It's almost exactly a copy of Buckingham Palace. Can you imagine somebody building a Buckingham Palace in the new world for science? I mean, so if you come and visit me, I can take you to a palace. I can show you a palace. Actually, if I showed you our laboratories, we have decorated ivy, or not ivory, sorry, ivory, some places inside the laboratory. So it's amazing. The building that you see on the very left of it is the house of the first Prime Minister of Canada. So Canada is a young country, and so you can remember where the first Prime Minister really lived, and that was where he really lived. We set up a joint lab between the National Research Council, which is the federal government's science laboratories, and the University of Ottawa and Attosecond, and we go to a new building in the University of Ottawa, about 2 kilometers separated from the old one. So it's about 2 kilometers between the two. And so that's the Advanced Research Complex, or we call it Jazz Lab South Joint, Attosecond Science Lab South. So that's the pictures that I showed you. And I guess that's all I'm going to tell you about Canada. It's a young country. Science was essentially just starting in 1929 there. I guess it had been used during the war, and this was the first laboratories built by the federal government. Before that, I guess Rutherford had worked in McGill before he did his famous work in England, but he had originally worked in McGill. And so McGill had science labs in Montreal, but University of Toronto, there was really no science. It existed, but there was no science there. I guess University of Ottawa existed, but I don't think there was any science there. So you see the beginnings of science. So now I've got 3 introductory slides to get going. So I'm going to go through them. They're really not about attoseconds, they're more general. But it struck me as I began thinking about speaking to a set of students here that maybe I had an assumption that you didn't. And so I start out with that assumption. And I think everybody working in short pulses has this assumption. So I just want to start out with it. So we assume that in order to make a fast measurement, all you need is a fast pulse. And if you have a fast enough pulse, you can excite something and then follow its motion and see how fast it is. And so that's a basic assumption. We almost never speak about it. And I didn't even put it in the talk until I began thinking, but not everybody in the audience will really buy that. So the way we do it, the way it's always done, this has nothing to do with attoseconds, is you do something with the first fast pulse, excite the sample in some way that it wasn't, cause a transition between 2 levels, or something like that. Then you see the response. You find a response. It can be, you can release an electron, you can release an ion, you can look at photons, there are all kinds of different things you can do. And you try to find something that a second short pulse will show a response. I showed you here, which I just simply took off the web, a change in the reflectivity of a material as a result of doing something. And that gives you somewhat the response. And you can get the response as fast as you wish, provided that the transition moment that got you started has the bandwidth to take it. Okay, so the drive And almost all of this science is to make a short pulse, and then you pretty well know you can use it. Okay, so I wanted to start out with that. Um, Probably all of you knew it to start with. I don't know. The second thing I wanted to start out with is to make a short pulse. Really, what you do is something you're very familiar with, even if you have nothing to do with short pulses, and that's interferences. You're familiar with it from courses where you do interference of two beams, and you see the two beam interference and all the interference patterns. You're familiar with it from water waves, because water waves interfere and you get big water waves and they cancel out in other places. And a short pulse is no more than an interference in time, just like those interferences you're used to in space. It's sort of not so often that you think of it that way, but that's what it really is. So I've got it, you can think of it even, I've got it even in Fourier transform way. I've got a set of 6 different frequencies, each frequency a little different from the next one. They're actually separated by a uniform part. I just made it up on the computer. And I phased them in such a way that at the center of the picture of the yellow ones, all phases are identical. All phases are the same. And simply I added them up, did an interference calculation. I added them up, and I get the time-dependent pulse that you see in red on the top. And so I just did interference, and that's exactly all that a short pulse is. There's nothing there. A minimum duration pulse has every frequency perfectly locked in phase with every other frequency. I mean, when I say it that way, it's amazing we can do it. When you say you can make a short pulse, somehow you get used to it and you don't think about what happens to it. So nothing, absolutely nothing, keeps this short pulse short. It will simply come apart by itself. So if you took a low intensity short pulse and you just let it go and propagate, well, there's nothing to hold it together. There's no reason to keep it together. The only thing that will keep it together is that if every color propagates exactly with the same phase velocity. And then the phase stays the same and the interference stays the same, but no material does that. So, so there's no force that keeps a low intensity pulse together. Maybe if you go really high intensities, you can find forces that's through nonlinear optics, through interaction with materials. But just ordinary light, nothing keeps it together. So it's very fragile in a sense. And we have to learn, when you play with short pulses, how to put them together and how to keep them together. And when they come out of sync, you have to put them back in again and correct it and so on. So that's sort of just some of the technology you learn. I'm not going to talk about it afterwards. We're still, all media that you go through, even as a short pulse, every medium, including air, everything, disperses a pulse, which means that different colors propagate at different phase velocities. And so a pulse that you have that's short pulse is only short as long as you propagate it through vacuum, carefully. And it's certainly not short if you propagate it through any medium. And so again, that's shown on an illustration in the bottom. And again, you must have to learn how to correct that for ordinary laser physics. And you want to deal with it in attosecond science. I'm going to show you in the next slide how you have to deal with it. But before I do, look what's happened. I took a short pulse, I went through a material, and I made a pulse in which the red ran ahead of the blue, which is what would happen in ordinary media for ordinary light. I made it so the red runs in front of the blue, becomes chirped pulse. It's called a chirp pulse, just like a bird goes chirp. I'm not sure I'm very good at this, so I won't try to give an example, but you can imagine. It's called a chirp pulse, and media tend to make one color go ahead of the other. Normal media and normal light gives you normal dispersion, which is what I've shown you there. The red outruns the blue. However, if I go to short enough wavelengths, the reason is that you got a resonance up here in normal media, which is transparent. So you got resonance up here, and the blue sees the resonance more and plays with it more than the red way down here. And so the red is less affected by the resonance, and so it propagates more quickly. And so that's the reason why it is. And so if you happen to get UV light, it goes the other way. Okay, so now I'm finished with all my introduction. I wanted to give these introductions so we all came to the same page. Okay, so let's start out. I want to talk about making an attosecond pulse. And if you understand this figure, which I'll take some time on, if you understand this figure, you understand everything I think about it. I'll give homework assignment because I know it's all students, so I figure there's no better place to give assignment than here. So I'll give a homework assignment afterwards. But look at it and you can understand it, I think, carefully. Yellow is light wave. So you can see the wave, light wave. Often it's 800 nanometers now because that's a good laser wavelength, 800 nanometer light. Its intensity is high enough in this figure that it will pull an electron free from an atom. Here it's shown a helium atom, 2 electrons. They're very classical electrons, and I'm going to give you a classical picture to start out with. And that will ground you in everything attosecond. So I'll go eventually to a quantum mechanical picture afterwards. Okay, the classical picture. So I tip this Coulomb potential by pulling on the electron, and I can always pull harder so I can force it to come free. And so when the electron comes free, it's near the peak of the field, because that's when the force is the strongest. It comes free. And now the electron starts to respond to the laser field and just move away, and the influence of the ion rapidly falls off, and so you can forget about the ion from now on. And now the electron's free, and so it gets accelerated away from the atom, and it may move 10 angstroms, right? So it's a long distance on the scale of an electron. So it moves out, gets lots of momentum, keeps going as the field turns its direction, moves up, another 10 angstroms, right? Something like that. Moves up, and then gets turned around, and depending on when it starts, it depends on when it turns around. If it actually tunnels or gets freed a little bit late in the phase, it comes back a little earlier, and if it gets freed right at the peak, it comes back, it starts coming back at the analogous position, the symmetric position in the wave in the other phase. And the electron comes back and collides with the atom from which it left. You could think about that, and I'll show you a better way to think about it a little while longer, that this electron comes back and recombines to the ion from which it left. And if it recombines, what does it do? It gives up all its kinetic energy plus all its potential energy to light, or to photon. And that's the high harmonics that we expect to see, that we do see. Not expect to see, that we see. Seems like an unlikely thing to do, doesn't it? But that's what it is. So depending now in its moment of birth, so it could be born any time in this field, but we're interested only in those ones after the peak of the field, because those are the only ones that come back and collide. So 50% of them just never collide again, and 50% come back and recollide. And of that 50%, we're interested in the ones after about 17 degrees, because those are the ones that come back and recollide, as I showed them on the picture. The other ones after that, you can find out if you solve F equals ma, come back in the last part of the phase, and they're left out for experimental reasons. We can get rid of them, so I think for this part of the talk it's sufficient. Okay, so now what happens? If the electron is born exactly at 17 degrees, it comes back here at the maximum energy it can have. And there's no reason why that's not 100 eV. It's typically 100 eV. So it's quite a lot for an electron. 100 eV electron would be 10 angstroms wavelength. So we've gone really quite short wavelength. It could be born a little later, you might say with less probability because the field is lower. But it's not completely zero probability, and it's got more probability of colliding. And it has a little less energy, so I made up arbitrarily 50 eV. And it could come back even earlier, and I made arbitrarily 10 eV. And you see a chirped pulse, a pulse that starts red, goes blue, or goes green, or goes orange, I guess here, and eventually blue. And so we've seen such a pulse before. That's why I gave you the first 3 slides. We've seen such a pulse before, and we know how to get rid of some of that chirp. And so we can get rid of the chirp by putting it through a material. So let me make it clear. We take an atom. It'll be a gas of atoms, of course. I'll talk about that in a second. We take an atom. We irradiate it with a laser beam, often 800 nanometers, usually a rare gas atoms. And then we get coming out of the other side a burst of radiation that goes from red to green to blue, but where red is 100 eV and blue is red is 10 eV and the blue is 100 eV. So that's gives you the bandwidth to make a very short pulse. Now, in order to make a short pulse, we need to put it through a dispersive material, but I already told you what that was. Ordinary material, when you're above the resonances, have the right dispersion to get rid of the chirpiness. So the shortest pulses are made this way, ensuring that there's only one chance for recollision. So a laser pulse can't do this more than once. One chance for recollision, which is the ones like I showed you there, and then put through a filter, and the shortest pulses are about 40 attoseconds now. Okay. Now I told you I would give you some homework assignments just to make sure you got it all. You can do this, I mean a high school student could have done this, so you didn't have to come to university to do it. I think you can do it in half an hour. And many people can do F equals ma more or less in their head. I tried to talk it through you. So why don't you take F equals ma, just Newton's law, linearly polarized light, so you know what the F is now completely. The velocity of the electron when it gets free is going to be 0 because it just barely makes it out. Velocity initially is going to be 0 at whatever time of tunneling. Ignore the ion after the electron tunnels, so forget about the Coulomb potential to keep it simple. And determine the final trajectory of the electron at time t equals infinity. And that will tell you what this electron will eventually do on a detector after your pulse is over. But you can get a whole set of trajectories, and you can see when it recollides, and you can reproduce the figure that I showed you just before if you wish. But now with different times of tunneling and F equals ma put in carefully. And you will get a set of energies of recollision, and those energies will be right, and they will have been exactly what you see in the field. And the times for the pieces of the electrons, the spectral phase will be right, and it will be exactly what you found in the field. F equals ma, amazing, isn't it? Okay, so it's really simple. And you can do it, I said, for 3 times 10 to the 14, because that's not an unusual number for this. Let me say the shortest wavelength that people have got are about a kilovolt, 1.2, 1.3 kilovolts of energy. That's using the highest ionization potential atom that there is, helium, and driving it with as strong a field as possible and making the field longer wavelengths, so you got longer accelerating and longer to push it back again, and therefore higher energy. Okay, so that's that's what it is. And I thought, well, now you're into homework assignments, so I'll give you 2 of them. So the second one is to do the same thing, but with circularly polarized light. Now you can solve it in your mind in a way. Imagine an electron that gets freed at circularly polarized light. There it goes, away from the atom. There's the ion. Goes away, but the field changes its direction, and pretty soon the electron trajectory is like that. So it misses the atom. Okay, it's way, way offside. So you can't make harmonics with circularly polarized light, but of course you knew that for other reasons. Anyway, just play with it. F equals ma. You'll really work, and you'll understand everything about this, including the way to measurement. And I want to say something about measurement in a minute. But before I do that, I want to correct what I might have left as the wrong assumption in your mind. If you take one atom and that's all you had, it would be kind of hard to find the signal in the X-ray. Probably you wouldn't be able to do it. The electron might miss, and so it might sometimes hit and sometimes miss. So most of the time there wouldn't be a signal, and once in a while there would be a photon, and it would be hard to see. So in practice, what we do is we take a whole set of atoms, we place them in a jet, but it could be in an optical fiber, it could be in a cell, it could be different things, it could be solids, it could be liquids, it could be many different things. So we put them in a cell, right there. We tend to use a supersonic jet because it produces a very cold medium of gases. It allows you to use molecules, and I want to talk about that when I end. Okay, so then I can do whatever I want to with the material that I have. As I said, it could be a solid. Everything is in the laser field, which is out here off the board. So you can make a laser pulse that's short. It can be a single cycle, so there's only one recollision, and that's the attosecond pulse that I showed you before, and I talked you through. Or you could have a pulse that goes on for a few cycles, and then you get an attosecond pulse, followed by an attosecond pulse, followed by an attosecond pulse, followed by an attosecond pulse, and that's the harmonics that you often hear about in the same context. And it's easy to see, and in fact there's a image of high harmonics of an argon atom, I believe it is, with a multi-cycle driver out here, and the harmonics are measured back there after on a spectrograph. But it could be only a single cycle pulse, because we in laser physics can now make pulses that are only one cycle long. Can you imagine it? Just one cycle long. Who would have thought you could ever do such a thing? But you can do it. One cycle long pulse, and in that case you only get one recollision, bang, one recollision and one attosecond pulse. And so that both of them can be done. And that's what's shown down here on the bottom. And because it's only one recollision and it's such a short pulse, it can be shorter wavelength. It can be, you push it harder if you like. The fields can be stronger driving it. And so you can see it goes up to maybe about 100 eV there, in that case from argon. And what you see in the vertical axis now has some information on it, because it's measured in a way that we can look at the spatial structure as well as the times, as well as the frequency structure of the pulse. Okay, now I want to go on and talk about measurement. But measurement is, you're going to be disgusted, I think, because it's no more complicated than what making it in the first place. It's really such an easy idea. Measurement is really the same thing as so what the measurement technique is, I think best is explained through a streak camera. Now, I don't expect hardly any of you to know what a streak camera is, and maybe nobody does. But a streak camera, I think, is still used by biologists and some people in the X-ray regime. So it's not unknown, but it's an old technology. So let me try to remind you, if you ever knew, what a streak camera was, and by extension then I'll tell you what we do to make it an attosecond streak camera and make the fastest measurements that can be made. Okay, so original streak camera had an optical pulse, you can see it here, coming in and irradiating a solid, a photoemitter, a photocathode, and the photocathode gave you an electron replica of the optical pulse. So out here, an electrons coming out would be something that's a replica of the optical pulse coming in. It wasn't a perfect replica, because photocathodes were never that good. You might free the electron from a photocathode, but maybe it came from different levels inside the solid state material. And maybe I suffered collisions on the way out because they were never a single layer. And that was, I mean, I think the replica was not so good, but it wasn't really bad either. So you can imagine such a pulse. Now that replica was moved with a strong field, and therefore in electrons there's all kinds of dispersion in electron waves, because different velocities of electron moves at different energy electrons move at different velocities. And so it was pulled out by as strong a field as you could get, and then the electron replica was deflected in deflection fields, which had a time-dependent electric field on it, just like the old-fashioned camera TV displays, where you deflected the beams back and forth with an electric field. Okay, so and then the first electrons in got deflected most, and the second electrons got deflected less and less, and so you saw the pulse as a streak or a smear across a detector on the back. You can sort of see how it must have worked, right? It wasn't so good because you couldn't put on the field very fast. The electron replicas weren't so good. Moving them over a distance was poor. Everything had problems. So, But what we did, we placed the photocathode with an atom. So now you sort of understand where the electron comes from, and you could choose, say, hydrogen. Maybe you wouldn't like to choose hydrogen, but in principle you could choose hydrogen. So it was as simple atom as possible, and there was no collisions in the way out. And we replaced the voltage, the time-dependent voltage, with a laser field. What's in a laser field? Laser going up and down. It's the electric field that goes up and down, right? So it's a time-dependent field, just like I put on with a deflection voltages. And that's really all there is to it. You could have looked at a deflection. We didn't. People mostly looked at the energy added or subtracted by a laser field. So the laser field took the place of the deflection plates. It could be placed right over the atoms so that there wasn't didn't have to move it. And then we measured the energy of the electrons. So that was all there was to it in a street camera. And a street camera is as simple as the other, and it can be understood with F equals ma. And it will get the right answer with F equals ma. You can do it more quantum mechanically, but the answer won't be much better. Let me just give you an example of how that's done. This is from our lab. We have a single beam coming in, which will ultimately make an attosecond pulse in here. We take a piece off of that beam, put it through a delay line, or put them both through delay lines, bring it back up again together again, and bring it in to a second jet where we make the photoelectrons. I'm not sure if these path lengths make sense, but you can imagine that they overlap, the pulses overlap as I described them to do it. And you get a image like this. It would be really a vertical cut through this image. But now, since we have perfect delay between the attosecond pulse and the field that's deflecting it, that's moving it back and forth, we can move it. We can move this delay line. See a delay stage written here, delay stage. And so we can move the delay line and get the whole delay on one side and the energy of the electrons on the other side. So we've taken a 1D problem and made it a 2D problem, and that's what's needed in order to use inversion algorithms. And so now there's an inversion algorithm that tells you everything you want to know about the attosecond pulse. It tells you every frequency, what phase it has, every aspect of the attosecond pulse can be understood in this way. And so this is the attosecond street camera, and it's used all throughout all of attosecond science. There's a version of it for attosecond trains, which is called Rabbit, but it's a photoelectron spectroscopy. It's a very similar idea. And so I won't try to tell you the differences in them all, but you can understand it completely by F equals ma. Okay, so, oops, not quite sure why that was. Okay, so now I think you know the technology, so you know how to make attosecond pulses, and you know how to measure attosecond pulses. The only thing that makes the technology hard is that it's in a vacuum. So vacuum systems are always a nuisance, but there's lots of other parts of science that deal with vacuum systems, so it's not unique here. That's the only thing that's really hard. So I thought I should give you one example of an attosecond measurement. It came out of Ferenc Krauss's lab. He's one of the people that won the Nobel Prize. It came out of Ferenc Krauss's lab, not out of our lab. Up until now, all the results were out of our lab, or else their concepts, which are my concepts. So he irradiated a solid material. I believe this was tungsten, but I didn't look it up beforehand. I think it was tungsten. So he radiated tungsten, and the electrons that came out of the tungsten, came from two different levels, or two different bands in the tungsten. And you can see that the characteristics of the electrons are slightly different around the 55 eV region and around the 80 eV region. Okay? And so he did exactly what I said, changed the time delay between the attosecond pulse and the sweeping field, and got the signal up and down, up and down, up and down, and he looked for the peak of these and saw, are they offset at all, one from the other? And he saw that they were offset by about 20 attoseconds, or maybe it was 100 attoseconds in this case. People have done measurements down to 20 and even 10 attoseconds this way, but in this way. And so And so he said that there's a difference in the time for an electron to come from one band of a solid and out and be measured, and from another band in the solid and out and be measured. And then, of course, it's up to theorists to think about what causes that difference. Is it because it was a difference in depth? Or is it because a plasmon was excited and some of the energy went into the plasmon or something like that? And so this is an issue that can be opened up by this kind of measurement for other parts of physics to consider and to think about. Okay? Okay, so I told you basically what would be the perspective of the theory that was developed in the 1990s for the production and the measurement of attosecond pulses, and the experiments that were done in the early parts of the 2000s. Okay, I'd like to just jump right away to a 2023-24 perspective. So high harmonics and attosecond pulses are the universal response of transparent matter to infrared light, to intense infrared light, and probably of metals too. So in our laboratory, we've looked at two different kinds of metals so far, and we see high harmonics from both. So probably it's the characteristic of all matter interacting with intense short infrared pulses that produce high harmonics. And so in some ways, nonlinear optics has to be modified and include this part in the final stage before damage occurs. Okay? It's a universal response, I would say, because the free electron that moves back and forth in the field, that's a real characteristic of any kind of matter. No matter what it is, electrons will always move back and forth inside of a field. And so it's not so surprising that it turns out in solid state physics, in dielectrics, and in other things, in metals. Okay? So the oscillating state is about Talbot-Volkov state. Now I'd like to give you a quantum mechanical perspective on this, and I probably should be speeding up, but I wanted to end up with a different thing which I also thought would be useful in a context of students, so I want to talk about this very much. But I'm going to give you first the quantum mechanical perspective, and then I want to talk about quickly the other part. So let me think about how you might think about it quantum mechanically, but only in words. I won't try to put it in complex equations. Okay, so what have we decided? What we talked about? We talked about having an electron bound in a Coulomb potential. So I sort of sketch what might be the wave function of such an electron. We talked about how the electron continues out and creates a wave packet. Of course, only a piece of the electron quantum mechanically goes out. A part of the wave function goes out, and a part remains behind. So having it the way I show it is probably about right. And so the electron goes out, but it goes out continuously or coherently, so that you understand the coherence of the electron wave packet that's out, as well as how it relates to the wave packet that's left behind. And of course, I can't show you without a movie or something like that, show you the electron moving and how it would go. But you could imagine, because we talked about how it would go and how it would go out and back again and how you would get a trajectory. So you'll have to put your imagination in this, or I guess since you're from Spain, you could think about a Picasso-like drawing. We used to be able to see one side of the face and the front and the side of the face simultaneously, and this was probably showing the Picasso-esque-like view of what happens to this electron wave packet. And when it comes back, it overlaps the wave function from which it left. Two portions of the same wave function. And this is how interferometry, this is how quantum mechanics works, that you add these two pieces of the wave function and we should see how it looks, right? So this is an interferometer. We've made an interferometer. We've constructed an interferometer from the electron of the atom or solid or molecule or whatever. We've constructed we've constructed an interferometer from the electron wave function. It's useful to think about, now I told you I'd give you another perspective on how the harmonics are really created. So when you think about this interference, and you think about the electron wave function coming in, the continuum one looks like a plane wave, or more or less like a plane wave, interacting with its former self, or portion of itself, that's left behind. Then I should see an interference. I square it to get the probability, and I find that the electron sits on one side of the atom. And if I wait just a fraction of a second, this fast-moving recollision electron moves forward a little bit, and now the interference has moved to the other side of the atom. And I square it, and I find out that the probability moves on the other side of the atom. And so the harmonics are emitted by this electron that moves back and forth, back and forth, back and forth, caused by the constructive interference. But that's just the dipole moment or the transition moment that you would study from quantum mechanics. I'm just giving you a picture of how it's done and how we can make that fully coherent. And so there is a wave function that sits. That's how you can think about it. Okay, so now I want to end up my talk, and I was trying to think what would be the most interesting thing for a group of students that would come out of Attosecond science. And so I will start out with the story, and then I will go off through, and it's related to this. So you could think about where you stand on measuring an orbital wave function. Some people argue that it's not possible to make such a measurement. Chemists would argue that. I think a first-year chemistry course frequently teaches students that orbitals are not real. They're just something a figment of your imagination that helps you design chemical reactions. So they're important, and they're important to study and important to learn, but they're not really real. There's really no electron in an orbital. And you can see why they would argue that, because the electrons are all the same. They can interchange with each other, and who says that the same electron stays in this orbital as it goes through something. Okay. Some others would argue that you couldn't measure a wave function, only the square. I think that's a better argument, but the first argument you should look at and think about and think where you stand on it, because this is a serious argument. I wanted to tell you a story about it. So right after we did this experiment, this comes from my lab, I was giving a talk in British Columbia, UBC, on an open talk associated with a big conference. And somebody stood up and said, I couldn't make such a measurement. This was irresponsible to be discussing it. And he was really disturbed, and he kept going and going and going on about this. And eventually he said he was going to write to the National Research Council and ensure that I was fired for making such a comment. Okay, so this is, so he felt very strongly about this. And I was about to give a talk to the Pacific Chem meeting in Hawaii, somewhat like this, I guess. A beautiful island in the middle of the Pacific, and of which there were about 5,000 chemists, and I could imagine many of these people having thought about whether orbitals were possible to measure. So now you should, with this introduction, I want you to look carefully at what I'm going to tell you and make sure that you see. But already I want to go back one slide and just make a point of this. I meant to make it as I was going through. And you see the motion that this electron interference has moved through. And so it's confined to the size of the bound wave function, right? It's moving back and forth on the scale. So already you see something to do with the measurement. You could imagine from this getting a measurement of the wave function, okay? So let me just talk around it. So when we have an interferometer, in physics, largely we try to move one of the arms of the interferometer. And you have a lot of availability to move the arms of the interferometer here. We can add another color to it and just add it on to the original one. So the original makes the basic interferometer, the other color moves it, just like a micrometer in the end. We could do it at another angle as well as coming in with a different frequency. Or in this case, where we take a molecule, we could take the molecule and take different projections of it, and that would be sort of like moving the arms of an interferometer as well. Okay, so we're going to take a molecule and move the projection of the molecule, move it around, and do a tomography on the molecule, just like tomography in a hospital would be done on you. Okay, so that's the idea. Okay, so just to make sure that you see it quickly and you understand it in your fingers, here's an artist's sketch. This is not mine. This is an artist's sketch of this experiment. Here's the electron coming back again You see the plane wave. You can see the bound orbital of the nitrogen molecule. That's what we use, a nitrogen molecule. It's got plus, minus, plus, if you happen to line it up correctly, and that's catching it where there's sort of a resonance in a way between the size of the size of the bound state and the size of the wavelength. And you can imagine going above and below the resonance, and that will be different colors. It will have just come from below and just going to above the resonance in that image. And now imagine what it would be as you turned it around, and think about this in your head, turning the molecule around and looking at it from the size. And it would be very different, and the interference would be very different. In fact, we do such an experiment. We take a molecule, send it from our supersonic jet, so it should be about 20 degrees Kelvin when it comes out. We take a pulse that's not ionizing but strong to create a potential well in which the line molecules tend to fall into. I can explain that to you in the questions if you wish. And that's done first with a small beam called pump, as whose intensity is about 5 times 10 to the 13 and focuses to a larger focal spot. And then we come in with a very strong beam that creates the ionization, creates the harmonics. And now we look for the harmonics, and we do this as a function of angle in the molecule. So I just showed you what a typical harmonics experiment would look like. We did this quite some time ago. We could do it better now, but well, I'm not sure. This is, aside from the introduction, I'm not sure what we can learn from this otherwise. So there's the harmonic spectrum for 5-degree intervals changes. The degree of alignment was shown in that earlier figure, so maybe you could say 5 degrees is a little optimistic for what we could achieve. However, that's what we see experimentally. We're essentially doing this. We're bringing the electron back again in different ways. And from that information and a tomographical reconstruction, which assumes no Coulomb potential afterwards, from a tomographical reconstruction, we see the orbital of nitrogen right there. That's the experimental value. And all we do is a tomographic reconstruction. It's from 19 angular projections. It's using a tomography method, just like you'd use in medicine. It's the wave function, not the wave function squared, although everything is referenced to itself. And so in some ways, still we don't know the phase because there is no such thing as an absolute phase. And this is out of a calculation for a 1-electron calculation and a multi-electron calculation. It's done, now we could do it with much shorter wavelength. We have not gone back to do it, but now we see the electron, amplitude, and relative phase. Okay, so that's something very unusual that comes out of this that isn't exactly attoseconds. And it seems to me it's a concept, and you might like to dig apart and tear it apart. I tried to introduce it so you could tear it apart if you wish. Okay, so let me stop. I'm sure that I've gone over what I should have gone. So as you know, this year's Nobel Prize went to Anne Lullier, Ferenc Krauss, and Pierre Agostini for attosecond science. So what have we achieved in attosecond science? We've extended the 50-year tradition of ultrafast science. So far, we've improved the time resolution of experiments by more than 2 orders of magnitude, because we can make pulses 2 orders of magnitude shorter. These are on the time scale of electrons, and this has been widely covered by the Nobel Prize. We've extended the 50-year tradition of nonlinear optics. There is a new part of nonlinear optics that really should go in there. It's not only Bloomberg and nonlinear optics that happens before damage, but there's this kind of nonlinear optics too, and it really should be put in. So we've extended this 50-year tradition of nonlinear optics by using Volkoff states. We open a whole new direction in gases, in dielectrics, in semiconductors, and almost certainly now in metals as well. So that's everything, I think. That's everything. And thirdly, we build on the 100-year tradition of X-ray science. We're pushing into the regions of synchrotrons. And they're pushing back with free electron lasers, of course. So it's a nice cooperation and competition with free electron lasers right now. And so we've extended the reach of lasers and laser physics by about 2 orders of magnitude into the X-rays. And of course, they've brought the intensity up of X-rays above what we can probably ever reach, but to synchronize it to something else is much more difficult for them. When I look at it and when I think about it, I think that we've been able to integrate small with fast, and that has to be important, and bring it onto laser physics and to something that's technologically accessible, it seems to me. And so I think that when I think about it, I think that there might be a real important home for this, not only in the kind of things that I've been talking about, atoms and things like that, but maybe in subcellular biology, where the size of organelles are the size of the wavelength that we can reach now with lasers. And so you can imagine doing laser physics on pieces of cells and, you know, desorbing them or transferring them or doing the kind of things that we think about in laser physics, but in biology in important sizes, or maybe in very small scale electronics, which is what electronics has happened now. And then finally, we contribute to the 100-year science of collision physics, because we've sort of built an amalgam between collisions and optics. And we can pick up some parts of collision physics. I mean, we're never going to go to Higgs bosons or something like that, but we can pick up some pieces and bring them into optical physics, and maybe they can pick up from us some pieces and bring time resolution into particle physics better. Okay, so that's I think that's everything I wanted to say. This is a picture of the group now, and I should leave it there, and I'll answer any questions.
Thank you very much, Paul, for your speech. It was very interesting. Now let's start the round of questions. Any questions?
Thank you very much again, Paul, for your incredible speech, honestly. And this is only just out of curiosity, but what made you study like Attosecond science for yourself?
That's a personal question, I guess. I was interested when I came to National Research Council first. So I was interested in laser physics, and I was there, I guess, when Donna Strickland and Gerard Moreau developed chirp pulse amplification. And I decided that lasers had gone as far as they were going to go in intensity. You can understand how to go more intense, but it was making bigger and bigger things. And with short pulses, they sort of went as far as they could go as well. People understood compression and things like that. And so there was time then to start thinking about using them for something interesting and important and unusual. And so that's, I guess I started for almost strategic reasons like that. That's me. I don't know why other people have, but that's why I did.
I see, thank you.
Other questions?
Hello, thank you for your talk. I have really enjoyed it. Forgive me if I'm a bit off topic, but during this year I started researching a lot of topics related to quantum mechanics because I'm doing my final degree thesis. And I came across the concept of weak measurement.
Oh.
And some of the ideas that you have presented reminded me of some of the experimental setups that are used in the weak measurement theory.
Yeah.
So I don't know if maybe you have some insight on how your research or the working Attosecond science can help understand what a weak value is, or maybe a weak measurement. And
so I don't know what to say. So I don't have a great insight into this, although I agree with you that there are things that remind you of weak measurements. So I think it's very perceptive of you to think of that so fast. I also think that there's must be overlap, and there are ways that are similar. I haven't thought about it for a while now. Jeff Lundin is just down the hall from me. He's one of the people that is important in weak measurements.
Yes.
And I've spoken to him a couple of times about it, but then we drifted apart and forgot about it again. So I don't have any good insight into this, but it's worth thinking about.
Okay.
There are so many things I left out of this. Weak measurement I wouldn't have put in no matter what. But there are quantum aspects to this, as you can imagine. There are aspects everywhere that I can't leave in 35 minutes. I can't put in. But that's a very interesting question.
Okay.
And I don't think I have a good answer.
Okay, thank you.
But it's an interesting question.
Thank you.
So maybe you'll have some insight.
Okay, thank you.
Other questions? Over there.
No. Thank you for your lecture. I thoroughly enjoyed it. I was wondering, when you transform your signal into photoelectrons and you measure the position of these photoelectrons, how, if you have a sequence of pulses, how frequent do you make these measurements? Because
I'll talk around this because I'm not sure exactly what you mean.
okay.
First, a sequence of pulses, when you Fourier transform and you look at it, is a series of frequencies.
Yeah.
So when you make a measurement, you'll see a series of frequencies. So the fact that it's a sequence of pulses and not a single pulse doesn't make it more easy or more difficult, I don't think. It's much the same. And that's why I only gave you one, and I said the other is sort of more or less the same. It's called rabbit. It's given a different name, but it's more or less the same. However, I can answer the question differently, and I'll try to do that too. Photoelectron spectroscopy is kind of hard, if you want me as a sort of a slightly external observer to tell you about. It's kind of hard because electrons don't like to be together, so you got to keep it low. And so the signals are low, and you want to fill in all of the spectrum. So they tend to be experiments that take a relatively long time. Maybe the early experiments took days. Maybe now I think they're pushed faster and faster, so you can do them in hours. But if you want to try to, so the field itself is trying to go towards a kilovolt or to high energies, 600 eV, 700 eV. Look at magnetic materials, look at speeds of response of magnets. And the cross sections get small, and so you have to worry about cross sections, hard to measure, and they're long measurements. So it's better to use another technique if you can use it. There is another technique which we're developing, but I haven't presented it here. And I would still say that this remains the gold standard. This is the way you make measurements best if you want to try to do it.
Okay, thank you.
Again, thank you very much, Paul.